Dr. Ali Amin is a lecturer at the Centre for Infrastructure and Engineering at the University of New South Wales. Dr. Amin graduated with a Bachelor in Civil Engineering with Honours Class 1 and the University Medal in 2011, and a Doctor of Philosophy in Civil Engineering in 2015, both from the University of New South Wales. Dr. Amin was recently awarded the CIA National Bursary Award for the Best Australian PhD dissertation in concrete and cement-based products and processes. Dr. Amin is a chartered professional engineer and also enjoys teaching at the tertiary level, having won a UNSW Vice-Chancellor's Award for Teaching Excellence in the Early Career category in 2016. Dr. Amin's research interests are in the structural analysis and design of high-performance and fibre-reinforced concrete structures.
In this webinar, I'll first talk about steel fibre reinforced concrete at the material constituted level. I'll then go on to speak about how steel fibres work with conventional reinforcing steels. Then, using this information, I'll go on to discuss how to go about describing some structural behaviour. So when we talk of steel fibre reinforced concrete, we speak of short, discrete steel fibres which are uniformly distributed and randomly orientated within the concrete matrix. Think of them as staples embedded within the concrete. Steel fibres can be found in tunnel linings and large jointless warehouse slabs. However, there is little uptake of the material in critical or suspended applications, as many practicing engineers don't quite know how this material works. If I were to load up a sample in uniaxial tension, it will behave almost linearly elastically up until cracking. If the material is made of glass, the response would drop to zero straight after cracking. Concrete will display a small amount of residual tension after cracking, and this is a function of the interlocking of aggregates at the crack. With steel fibre reinforced concrete, the fibres become engaged and bridge cracks once they form, and provide a wonderful toughening behaviour after cracking. After cracking, we express this behaviour in terms of a stress versus crack opening displacement relationship. The shape of this part of the curve is a function of the amount of fibres added to the concrete, the type of fibre, and the strength of the concrete. The question then is, how can we experimentally go about obtaining this curve, as this relationship is required to quantify the effect of the fibres in structural applications? And there are three main ways we can do this. The first is through a 3 or 4 point notched or unnotched prism bending test. The second is through a uniaxial tension test, and the third is through a determinate round panel test. And each of these tests have their pros and cons. The notched 3-point bending test is a relatively easy test to perform, and most laboratories have the capacity to conduct this test. But there's usually a large amount of scatter associated with the test results from this particular test. The uniaxial tension test is the most direct way of obtaining the stress versus crack opening displacement relationship for steel fibre reinforced concrete, but there is much conjecture in the scientific community on the use of direct tension tests for concrete. The first is the nature of the test setup and how the specimen is attached to the testing rig. The second is that these tests are costly in time and require specialised equipment. The round panel test specimen is a relatively large specimen, which has a diameter of about 800 millimeters and is approximately 75 millimeters thick, and therefore is quite heavy and difficult to handle. But with the formation of 3 fracture lines, scatter in these tests is typically low, and hence characteristic values can be high. For the prism bending and round panel tests, some sort of mechanism is required to convert force displacement data to stress versus crack opening displacement. This process is called an inverse analysis, and as you can imagine, the interpretation of these results hinges a lot on the inverse analysis process. Once we have the stress versus crack opening displacement relationship for fibre reinforced concrete, we can then start to look at a simple bilinear model for use in structural design. About the time I started my PhD, the FIB Model Code 2010 was released, and in there contained provisions for the use of steel fibres and concrete. The FIB Model Code also contained an inverse analysis procedure which was capable of converting notched 3-point prism bending test results to uniaxial tension. Essentially how this is done is by computing the residual flexural tensile strength at certain indices along a prism bending test, and then assume a predefined stress versus crack opening displacement relationship, which then feeds into equations shown on the right. More information can be found on this model in papers written by Professor Marco De Prisco at the Politecnico di Milano. One important item to note is that when we talk of crack widths at the serviceability limits and ultimate limit states, we speak of crack widths of 0.5 millimeters at the serviceability limit state and 1.5 millimeters at the ultimate limit state. And I'll come back to these numbers in a second. To validate the model, we conducted a relatively large experimental campaign in which we tested matched direct and indirect tension tests using a wide range of fibre types, fibre quantities, and concrete strengths. The photo at the top of the slide shows our prism bending test rig. The prisms are usually typically 150 millimeters square in cross section and span 500 millimeters. The specimens have a notch 25 millimeters at their mid-span. And the prisms were tested in a closed loop system by fixing a clip gauge to the underside of the beam at the notch to measure and control the crack mouth opening displacement at the soffit of the prism during testing. The uniaxial tension tests shown at the bottom were conducted on hourglass-shaped dog bone specimens. The geometry of the test specimen is about 40% narrower in the midsection than at its ends, and permits for failure to occur of the sample to occur within a reasonably well-defined region. Furthermore, there are no notches in this test specimen, and so the dominant crack does not pass through a predetermined plane. To measure strain, hence crack opening displacement, transducers were placed on each of the four sides of the specimen, and these deformations were continuously recorded during testing. The specimens were tested using ram displacement control, initially at a rate of 0.12 millimeters per hour until the formation of the dominant crack, and then we progressively increased this rate as the crack widened. In this slide, we have some sample test results of 60 millimeter end hooked fibres at a fibre dosage of about 65 kilograms per metre cubed. On the left, we have the uniaxial tension test results, and on the right, we have the 3-point notched prism bending test results. On the left, the black dots on the vertical axis represent the cracking strength of the concrete, and it's important to note that with the addition of fibres to concrete, the fibres have very little influence on the tensile strength of the concrete. After cracking, there was a sharp reduction in load, which coincided with significant opening of the crack as the elastic strain energy in the system was recovered. Once the crack had stabilised, it was clear that there was no direct contribution by the concrete and that the load was resisted wholly by the fibres. As the test progressed, there was a reduction in load with increased crack width, which is expected from strain softening materials. In the prism bending test, we had an elastic phase up until cracking, which was then followed by some flexural hardening, and then finally a reduction of load with increased CMOD. Again, this is what we expect from a softening material. In this slide, I've plotted the results of the FIB model code inverse analysis procedure along with the direct tension test shown in grey. If we look at the comparison of the results at 0.5mm and 1.5mm, we see that the FIB model code consistently overpredicts the strength offered by the fibres, and this is unsafe. We then took a blank canvas approach and started studying the response of a prism in bending. We made the following assumptions. 1, that we ignore the tensile component of the uncracked concrete. 2, that we assume rigid body rotations. And 3, that failure occurred over a single dominant crack. Again, what we expect from a strain softening material. With these assumptions, we first developed a generalized expression for the average crack width in a prism, which is a function of the CMOD, or the crack mouth opening displacement, which is what we physically measure during testing, and the geometrical characteristics of the beam, where big D is the depth of the prism, HSP is the depth minus the notch depth, and DN is the depth of the neutral axis, which I'll come back to in a minute. Using mechanics, we also derived an expression for the residual tensile stress carried by the fibres as a function of the applied load and the geometrical characteristics of the specimen. It's important to note that these expressions can be used for any size prism. Going back to the depth of the neutral axis, we conducted some non-linear fracture mechanics and showed that the ratio crack opening displacement over crack mouth opening displacement was insensitive to the neutral axis depth. And so we could simplify the equation on the previous slide by conservatively assuming that the depth of the neutral axis is fixed and equal to 0.3 times HSP. If we want to develop a simplified expression of this model for use in design, it's important to think about what is actually going on during the test. In the prism test, it's important to recognize that at early stages of the test, after the matrix has cracked, the matrix component to the resisting moment is significant when interpreting the moment versus CMOD response. At later stages of the test, as the crack widens and the neutral axis rises higher up in the section, the influence of the matrix component becomes less and less significant. So in determining a simple model, we have adopted points corresponding to CMODs of 1.5 mm and 3.5 mm. These points are selected to be sufficiently separated from each other to provide reasonable modelling over the most important region of the stress versus crack opening displacement curve for both the strength and serviceability limit state designs, and with CMOD of 1.5 being sufficiently distant from initial cracking that the contribution of the uncracked concrete to the sectional capacity of the prism is small. With this, we have the following simplified equation as a function of FR2 and FR4. Here I've plotted the results of the inverse analysis procedure of the FRB model code along with the proposed model and the uniaxial tension data. If we look closely at the key points of 0.5 and 1.5 mm, we can see a good correlation between the proposed model and the uniaxial tension test data. We have since extended this model to the round panel tests, and as can be seen at the bottom left, we are getting really great correlations with the test data. Just on the issue of this idea of toughness, the residual tensile strength of the round panel test specimens has traditionally been expressed in terms of joules, which is the area under the load versus central displacement curve. However, over the last decade or so, design methodologies have moved from defining the post-cracking strength of fibre-reinforced concrete from the area under the load versus displacement curve to defining the toughness of fibre-reinforced concrete in terms of the residual tensile strength resisted by specimens at various stages of the test. Consider, for example, the response of the curves on the bottom right of screen. Both curves give the same area under the curve, but clearly have different responses. The next part of my PhD looked at how steel fibres interacted with conventional reinforcing steels. It's important to note that in most practical applications of steel fibre reinforced concrete, fibres are co-reinforced with conventional steel. So suppose I constructed two rectangular prisms of concrete, one with fibres and one without, and both with a concentric steel reinforcing bar, just like the photo on the right, and loaded them in tension. I would probably observe a couple of key things. The first is that the cracking strength of the tension tie would be about the same. That is, the addition of the fibres won't affect the cracking load of the specimen. As we apply more and more load, we will notice visibly finer and more dispersed cracks in the fibre-reinforced concrete sample than the plain concrete sample, even at loads close to yield strength of the steel. This behaviour is highly favoured, as we would prefer to have many finer cracks than just a couple of wide and unsightly cracks. Looking at the models that describe this behaviour in the literature, found that most of these models were fairly empirical in nature. When describing the tension stiffening behaviour of reinforced concrete, it's hard to go past the tension chord model out of ETH and Zurich. In this study, we modified the original tension chord model to include the beneficial effect of the fibres. And essentially what this means is that the tension is carried across the cracks through the fibres, and consequently the strain in the steel bar is less than what it would be if the fibres weren't there. To come up with an equation which describes the tension stiffening relationship of steel fibre reinforced concrete, we considered two extreme hypothetical cases of crack spacing. On the left, we have the maximum crack spacing scenario, and on the right, we have the minimum crack spacing scenario. The maximum crack spacing scenario occurs when the section between two primary cracks is at the onset of cracking. The minimum crack spacing scenario occurs when this section cracks, and no more cracks can form as a result of the buildup of tension through the tension tie via bond. The expression on the left represents the average tension going through the tension tie at the maximum crack spacing scenario, and this is a function of the tensile strength of the concrete and sigma F, which is the stress that's carried by the fibres at the crack. Similarly, presented on the right is an expression for the average tension through the minimum crack spacing scenario, also as a function of the cracking strength of the concrete and the stress carried by the fibres at the crack. Over many cracks, taking the average of these two extreme scenarios gives our proposed expression for the tension stiffening relationship for fibre reinforced concrete, shown at the bottom of the slide. In this slide, I've compared the proposed model with the test data we obtained at UNSW, as well as from the University of Brescia and from the University of Toronto. And as can be seen, the model predicts the tension stiffening response very well, even when we account for things like shrinkage. Once we have this tension stiffening relationship quantified, we can then start to look at the verification of the serviceability limit state, namely in the evaluation of crack spacings, crack widths, and deflections. With the stress distribution in the concrete and steel known, then the crack widths are simply the difference between the steel and concrete elongation between the cracks. Plotted in the top right is our crack width model plotted against some experimental data, which shows an excellent correlation. We can also start to look at the effect of increasing fibre dosage. On the bottom right, we have predictions for specimens with 25 and 50 kilograms per metre cubed of steel fibres, and we can observe a significant reduction in crack widths when we add more and more fibres. Again, with the tension stiffening relationship quantified, we can start to develop rational expressions for deflections of fibre reinforced concrete beams. Here we can take the instantaneous deflection of a beam equal to the deflection, assuming the entire beam is fully cracked, and subtract the stiffness provided by the uncracked concrete and the stiffness provided by the fibres at the crack. As can be seen from the figure at the bottom right, the model predicts the experimental results very well. Moving on to structural behaviour. In the literature, the domain of shear is probably the main area where the effect of adding fibres to concrete has been most studied. Surprisingly though, when I started my PhD, there were no studies which reported the response of fibre-reinforced concrete beams with stirrups failing in shear, as both fibres and stirrups increase the shear capacity of a beam. Many tests reported that the combination could change failure from a brittle shear failure to a ductile flexural failure, which is true, but these could not be these tests could not quantify the effect of each of these means of reinforcing. We conducted a very large-scale experimental program where we manufactured and tested 10 5-metre long, 700mm high and 300mm wide beams. The beams had a shear span to effective depth ratio of 2.8. This value was selected to minimise any effects due to arching. The longitudinal steel ratio was 1.98%, which is slightly high but does meet code requirements. This high amount of steel was chosen to ensure that the strain developed in the steel bars would remain elastic and not induce yielding. 2 fibre dosages were adopted, and they were 25 and 50 kilograms per metre cubed of the Dramix 5D double end hooked fibres. Here are some photos taken from our lab. On the top left are some of our reinforcing cages. On the top right shows us adding fibres to the back of the concrete agitator and allowed the concrete to mix for 10 minutes. During pouring, we would fill up cylinders of fibre reinforced concrete and wash the cement paste and extract the fibres using a magnet. We would then dry the fibres and weigh them. This was done to ensure a uniform distribution of fibres during the casting procedure. On the bottom, we have a bunch of material samples. On the top left here we have beams just after casting. On the bottom left we have a beam in our frame prior to testing. On the top right we have a beam with a beautiful shear crack, and on the bottom right we have a dog bone which form part of a complete material characterization study on the beams. In this slide we have all the details of each of the beams. The beams had varying amounts of fibres and transverse stirrup reinforcing steels, and we cast them over 3 different batches. Here are the test results of our beams. The cracking shear load ranged from 80 to 110 kilonewtons. The bottom layer of steel yielded slightly only for the most heavily reinforced concrete beam. If we compare the results of B25000 and B0450-10-450, we would notice that the peak load of the beam with 25 kilograms per meter cubed of 5D fibers only compares reasonably well with the beam reinforced with the minimum required shear reinforcement. However, after peak load, the beam with just fibers shows a significant drop in load, whereas the beam with stirrup shows a relatively long tail. Again, something to consider when designing beams with just fibers. These are some crack patterns of the specimens, with all displaying really great shear cracks. We observed some peculiar behaviour, however, with the specimen containing only 50 kilograms per meter cubed of 5D fibres, with lots of damage on one side and very little damage on the other side. So we decided to clamp the damaged side, pre-tension some threaded rods with some load, and then test the other section of the beam. The second failed side gave us a result we were originally hoping for, and we noticed that the number of fibres in the originally failed side was significantly lower than expected. This highlights the fact that even in well-controlled environments such as in our lab, we may still violate our assumption that the fibres are well distributed within our samples. In 2010, Professor Foster developed a sectional shear model based on the simplified modified compression field theory out of the University of Toronto for the case of fibre-reinforced concrete beams without stirrups. In this study, we adapted that model to include the effect of the stirrups to shear. The total shear that is resisted by the section is equal to the shear resisted by the concrete, added with the shear resisted by the stirrups, added with the shear resisted by the fibres. It's important to note that the concrete and fibre components are coupled as each is a function of the critical crack width, and that is the concrete via aggregate interlock and fibres through bridging action. The concrete and stirrup components are taken straight from the simplified modified compression field theory, and the contribution of the fibres is essentially the stress carried by the fibres averaged over the area of the crack. This model requires a couple of rounds of iteration to solve for the crack width. To simplify the iteration procedure, AS5100 considers the stress carried by the fibres at a crack opening displacement of 1.5 millimeters, but the model still preserves the 3 components to resisting load as shown. The FRB model code contains shear provisions for one-way members, which came out of the PhD of Minelli from the University of Brescia. The model is an adaptation of the Eurocode 2 model for shear, which essentially treats the fibres as additional longitudinal reinforcing steel, which is mechanically or physically incorrect. This table shows the results of the 3 models, and just drawing your attention to the bottom of the slide, we can see that we're getting very good correlations with the AS5100 and Foster models, and we're a little bit off with the FIB model. We conducted a bunch of numerical analyses using the commercially available finite element package Athena 2D developed by Savenko Consulting out of the Czech Republic. The adopted material model was based on a fracture plasticity approach, fracture to describe concrete and tension, and plasticity to describe the concrete and compression. And provided we inputted the stress versus crack opening displacement data from the material characterization tests. We observed excellent correlations with the test data. To conclude, fundamentally, we must correctly establish the post-cracking residual tensile strength offered by the fibres if we're going to correctly design steel fibre reinforced concrete elements. At the elemental level, the tension chord model was successfully adapted to include the beneficial response of the fibres across cracks. And once we know or can quantify the tension stiffening relationship of fibre reinforced concrete, we can then determine with confidence things like crack widths, crack spacing, and deflections, which are all required for serviceability limit state design. Finally, beam shear was predicted reasonably well with models that we developed during this study. Thank you very much. So I hope you enjoyed the webinar today. Please feel free to reach out. I'll be more than happy to answer any questions you might have, and please contact the CIA to get my contact details.